All right, hello. So today we're going to be talking about an example of using the variational method. We're going to use the methods to try to estimate the ground state energy of helium.
Okay, so I have to confess that was virtual helium. We're going to nevertheless do what I said. So the prerequisites for this video are that you know about the variational method. So you may want to review the video on variational method, practical summary, and tips. And the other prerequisite is just to know about the ground state wave function and energies for hydrogen and hydrogen-like atoms. So let me just review that. So to start with, what is a helium atom? So a helium atom is a nucleus. So this is an alpha particle. It's 2 protons and 2 neutrons. But for our purposes, we can just think of this as a point particle with a charge of +2. And then we have 2 electrons. And so I've drawn here a classical version of this, so a classical picture of our helium atom. So before we start, though, let's actually imagine a simpler scenario. We're going to imagine what's called a helium. This is a helium plus ion. So this is just the nucleus and 1 electron. And so it's useful to know that understanding that atom or that ion is no different than understanding the hydrogen atom. So the same methods can be used to solve the differential equations that you get when you're writing down the time-independent Schrodinger equation. And we can write down the wave function for the ground state, and it looks very, very similar to the wave function for the hydrogen ground state. Okay, so I will just remind you that so the ground state wave function, let's say we have a general z, so here z equals +2. Z is just the number of protons in your nucleus. And so in general, if you have a nucleus with z protons, then the ground state, and you have just 1 electron, then the ground state wave function for that electron, it looks like psi100 of r, and then it's equal to e to the minus zr over a. So z equals 1 for hydrogen. Now it's z equals 2, but this applies to any atom with any number of protons. So that's the function. It's just an exponential decay in the radius. But then we have to multiply by a normalization constant, and that turns out to be square root of z cubed over pi a cubed. Remember, a is the Bohr radius. And so that normalization constant is there so that the integral over all of space of the square of that wave function gives 1. And if you work out the corresponding energy eigenvalue, then it turns out that it's just minus 13.6 electron volts, but now it's times z squared. Okay, so physically what's happening is that because you have that extra charge in the nucleus, so there's a larger attraction between the electron and the nucleus. The electron ends up closer to the nucleus. This binding energy is larger, and so the overall ground state energy is going to be lower. Okay, so now let's talk about actual helium. So I will restore, well, I wanted that to be red. I want to restore the other electron. Okay, so now we have 2 electrons in our helium atom, and so now let's think about that as a quantum system. Okay, so again, we're just treating the nucleus as a source for an electric field, and so it's going to come into our problem just as part of the Coulomb potential for the electron. So we're thinking of our quantum system as just being two electrons interacting with each other and interacting with this Coulomb potential. Okay, so first to describe that quantum system, now it's a two-part system. So we have two electrons, and so we can write a basis of states for that system, the position basis. And in the position basis, each of the two electrons would be at a definite position. So I'm going to write that as R1 for the first electron and R2 for the second electron. And so that's sort of a hypothetical state where the two electrons each have some definite position. Okay. All right, position. Okay, now actual states of helium are going to be superpositions of those basis elements. And so to describe a general superposition, we need to say, what is the coefficient of each of those basis elements in our superposition? And so what we're going to need is one number for every pair R1 and R2. And so that means the wave function describing two electrons in a helium atom is a function of these two vector position variables. Okay, so our general state we're going to describe by a wave function psi of R1 and R2. Okay, and so the full state in the Dirac notation would be some integral over R1 and R2 times that wave function times this position basis element. Okay, what about the Hamiltonian? So we're going to ignore spin. We're just trying to get the kind of 0th order approximation to the energy of helium. And so if we think about the Hamiltonian ignoring spin, then it has various pieces. And actually, this would be a good point to stop the video if you want and think about, can you write down what the Hamiltonian for these two electrons in a helium atom would be? Okay. And then come back after you've thought about it. Okay, so let's talk about that. So in the Hamiltonian for helium, there are some terms that just refer to the first electron and terms that just refer to the second electron, and then there's terms that involve both of the electrons, and those are the terms that describe the interaction between the two electrons. Okay. And so let's write those down. So first we can think, well, if we just had one electron, then the Hamiltonian for that would look like the hydrogen atom Hamiltonian. So that would be P1 squared over 2m, and then plus the potential term, which is just the Coulomb potential. So V Coulomb, Z equals 2 of R1. Okay, and so that one, just to write that explicitly, so that would be minus 2 E squared over 4 pi epsilon 0, and then 1 over the magnitude of the vector R1. Okay. So those are the terms in the Hamiltonian that describe the kinetic energy of the first electron and its interaction with the nucleus. Then there's a similar term where you have the kinetic energy of the second electron and the Coulomb potential term for the second electron, and so that's the potential energy of that second electron in the Coulomb potential of the nucleus. Okay, but finally we have an important term, which is the term that tells us about the repulsion between the two electrons. Okay, so there is a Coulomb energy that I'm going to write as VEE. So that is a potential which depends on the position of both the first electron and the second electron. And so that's just going to be equal to E squared over 4 pi epsilon naught. So it's again just the usual Coulomb potential, except what comes into it is the distance between the two electrons. So this is the absolute value of position of electron 1 minus position of electron 2 in the denominator there in our 1 over r Coulomb potential. Okay. And so it'll be useful for us to write this all as H1 plus H2 plus VEE. Okay. All right, so now how do we think about the ground state of this atom? So one thing to note is that if we didn't have the interaction between the two electrons, then this would actually be a very simple problem. So let's think about that. So if no VEE, if you want, stop the video, think about what would be the ground state energy in that case. Okay, so that case is really simple because if you think about it, then our Hamiltonian without VEE is just two separate terms. There's H1 for the first electron and H2 for the second electron. And so that's the same Hamiltonian as if we had two completely separate helium plus ions. Okay, so H is the same, ooh, I got blue, as for two separate helium plus ions. And so as a result, we can completely understand what the wave function would be. So the wave function, or the state, is just going to be the ground state for that first electron and then the ground state for the second electron. Okay. And in terms of our wave function, that means that the wave function of R1 and R2, it's just the product of psi 1, 0, 0, z equals 2 for the first electron, and psi 1, 0, 0, z equals 2 for the second electron. Okay. So that would be the ground state wave function. The energy would just be double the energy for the single helium plus ion. And so that would be minus 13.6 electron volts times z squared, which is in this case 2 squared, and then times 2 because we have the two different electrons. And so that works out to minus 109 electron volts. Okay. Now you might think that would be a decent approximation to the actual energy of the helium atom. Maybe this interaction between the two electrons is something like a small perturbation, and now we could do perturbation theory to understand the effects of that. Okay. Unfortunately, it's not really a small perturbation at all, and we can really understand that just from the structure of the Hamiltonian, that we have a certain energy. Let's think about the Coulomb interaction between the electron and the nucleus. That's a certain amount of energy, but the electron-electron interaction is basically just looks like that again, with a factor of 1 instead of a factor of 2. So the energy there is a similar order of magnitude. If you have these two electrons inside the atom, then the distance between those two electrons is going to be of the same order of magnitude as the distance between the electron and the proton. Okay, and so the summary is that with VEE, it turns out that, well, there's just no way to solve the problem analytically. And perturbation theory is not going to be useful for us. Not useful. Okay, and so we need another technique, and that technique is going to be the variational method. So we're going to use the variational method. Okay, and so in the next video, we'll see how that works, and we'll see what kind of trial states we can think of to try to accurately estimate the ground state energy of helium.